Electrons which are very close to the nucleus, not in the nucleus. In the nucleus there is no electron. Electrons which are close to the nucleus or the very close to the nucleus means in the first orbit. Okay, they are said to be core electrons. What are valence electrons?
Electrons in the outermost.
Electrons in the outermost shell are known as valence electrons. What is valence band?
It is a group of electrons and a group of valence electrons.
Yeah, band formed due to the valence electrons.
So can you give us some idea of what it was?
Yeah, that's what I'm saying. Were you not there?
Because I'm still sleeping.
Also time.
Okay. I'm starting from
At least
there.
I can say that I'm coming.
See, we
late.
discussed.
Well, like,
Okay. See, what we have done in that. No, again, if I don't start, no, then he will not allow.
Sir, I'll teach him afterwards, sir.
Yeah, but by that time I have to vary.
So we'll teach him afterwards.
That's good.
So I don't care about it.
Okay, just
on the starting, sir.
yeah, the definition. See, we started with types of material. That is, what is a conductor, insulator, semiconductor, dielectric material, and superconductors. So, what are the differences between these material and what are the examples, and what is the behavior of this material? We discussed about it. Second thing is, we discussed about the classification of semiconductors. And semiconductors, classification is pure and impure. Okay, pure means intrinsic, impure means extrinsic. And extrinsic we have again N type and P type. Here N type and pure means silicon and germanium.
Okay.
Now we have also classified the material like third A group element, fourth A group element, and fifth A group element.
Okay.
Third A group element is also known as 13th group element. Fourth A group element is known as 14th group element, and fifth group element is said to be 15th group element. 13th is having 3 electrons in the outermost shell. 14th is having 4 electrons in the outermost shell, and 15 is having 5 electrons in the outermost shell. And 14th one is known as a pure semiconductor because it is tetravalent. Okay, tetravalent. Whereas next is doping. So we have elements. What are they? In third group element, boron, aluminum, gallium, indium, thallium. Boron is a gas and thallium is a radioactive element. And fourth group element, carbon, silicon, germanium, tin lead. Carbon is a gas and lead is a radioactive element, the end product of the radioactive elements. And fifth group element, nitrogen, phosphorus, arsenic, antimony, and bismuth. Nitrogen is a gas and bismuth is again a radioactive element. So that is why only these 3 elements in each group is taken into consideration. So when doping means addition of impurity to a pure semiconductor is said to be doping. Okay, how much is the ratio of doping? 1 is to 10 to the power of 8. That much is the doping. Now, very very small. That's what. So very very little doping. Doping means not like too much. Okay, just addition of impurity to a pure semiconductor. Next, then we have we are adding a third group element to fourth group element to form a p-type semiconductor. Third group element to fourth group element. Okay, to form a pure semiconductor. Sorry, to form a and p-type semiconductor. So when you form one, every time we get a hole. For every combination we get a hole. Whereas for n-type semiconductor we get a electron, excess electron. Okay, so the charge carrier in n-type semiconductor is an electron, and the charge carrier in p-type semiconductor is a hole. Understood now? So next one, we drew about the energy level diagrams. The energy level diagram for p-type, sorry, for conductor.
Overlapping.
Oh yeah, conductor in overlapping and n-type and p-type also. In conductor, semiconductor, insulator first we drew. Conductor, conduction band and valence band, they are overlapping. What is conduction band? The next higher band to the valence band is said to be a conduction band. Means if the electron has to run or flow or it has to conduct, then the electron which is in the valence electron has to come to the conduction band. Then only the passage of current takes place. Understood? Now next one is there are 3 energy level diagrams we discussed. In the conductors, the conduction band and valence band, they overlap each other. Whereas in semiconductor there is a small gap. How much? Less than 3 electron volt. Whereas for insulators it is greater than 3 electron volt. Okay, so maybe 6 electron volt also. Now again, if we come to this n-type and p-type semiconductor, there is a Fermi level in between. What is it? It's a line. That line is said to be a margin is given there. Fermi level. In n-type semiconductor, this Fermi level is very close to the conduction band, and whereas in p-type semiconductor is very close to the valence band. Okay, why? Because there is excess charge carriers in n-type semiconductor and there are excess number of holes are in the p-type semiconductor. But keep that in the mind. When we say hole, it doesn't mean it will move. Actually, it is exactly the opposite motion of the electron. Holes, electrons can move from one place to another place. Hole is a vacancy created when electron moves forward. Okay, that means exactly electron and hole they are in opposite direction. Understood now? Is that clear?
So could you tell an example for p-type semiconductor?
Yeah, p-type semiconductor is a combination of fourth group element and third group element. Like you can say silicon, galide, silicon, galide, like that. Understood? Or germanium galide, germanium, what you call silicon, aluminate, like that.
So the first and last won't be there. First and last element.
Gas and radioactive.
First is gas and last one is radioactive element. So we don't take that into consideration. Maybe the isotopes of that are maybe we can take that also. But we don't go exactly to those because we don't have radioactive headache now. We already have studied about the nuclei, right? Again they have a half-life, that headache is there. Again gas is you cannot form that means the substance has to grow one over the other. How will the gas grow on the other? Gas is having a evaporation, that is escaping condition situation. So it's a problem. So that is the reason we don't use the first and the last one. Got it? Chalo. Now we will go to one of the important parameters, that is about the Ne and NH and Ni. On this there can be a numerical. Generally semiconductors will not ask any numericals. But if there is any iron leg in our center, then it can be. You know what is iron leg?
One in metal.
There will be. Maybe we don't know. Okay, so better we will do the complete chapter. And anyways, it is only not much. Transistors are not there. They are not diode also they have removed. And the gates also they removed. Actual thing of the crux of the chapter is almost deleted from the thing. Okay, so you have very less portion from the semiconductors. But it would be better if you would have studied this transistors and all, because even if you are not going with the engineering or something else, at least that information would have retained with you for a long time. Understood? So anyways, so sir, do they ask working of LED, solar cell? Yeah, definitely they will ask. Okay, out of these three, one will be definitely in the examination, either solar cell, LED and photodiode. Again I am telling you, in that also solar cell can be mostly, because there is a OR question actually. So definitely there can be a solar cell. Solar cell, why they are expecting? Because in most of the cities in India we are going with solar street lighting system. So that may be the reason why they are asking this question, solar cell. Okay, so definitely read all these three, learn all these three. So definitely one will be there. What is there exactly? First of all, what is a solar? Example, if there is a solar cell, they are asking what is a solar cell? What is the function? Okay, solar cell means it converts solar energy into electrical energy. That's the actual definition. Then, no, I will explain that, don't worry. So, let me first explain the PN junction diode and the VI characteristic of PN junction diode, working of PN junction diode. Once I am done with that, then I will go with this the remaining chapters, the remaining topics. Okay. So, I want to give a glance what exactly is. So, what exactly we have to write there in solar cell, LED and photodiode is first you will write the definition, what exactly is LED or solar cell or photodiode. Then you will draw the diagram, the construction. Okay. Then you will explain the working, construction, then working, then its uses. Okay. Clear? Especially in if you go to LED, it tells about the composition. See, we have LED of red color light, green color light and blue color light, right? So it depends upon the amount of composition. Like GaAs A3, GaAs A3. I think there is a substance, gallium, arsenic, aluminum, something. So we have, what we do is there is a composition 0.321, some composition there. If you want the color, it depends upon that composition. What type of LED you want, it depends upon the composition of those elements. Okay, ratio of the elements. Now in LED, and you have to explain the advantages of LED. Okay, and the diagram of LED. Suppose if there is a graph, you need to draw a graph for LED. Same way it happens in the solar cell and also in the photodiode also. What is LED? LED is a device which converts electrical energy into light energy. Best example is a remote control. The remote control has a small light or a small lamp at the end like this here. You might have seen here. So, but there is an infrared region. You cannot see when you press the lamp. When you press the switch, you cannot see any lamp here because it is an IR region. It's an IR region. So there is a LED. Okay. So LEDs are also red in color. On the top of the buildings we have LEDs. Okay. And coming to photodiode, photodiode is the receiver actually. In the TV there is a small lamp. When you press on switch on this one button, then there is a small blinking. So that is actually there is a photodiode. There is a receiver actually. Photodiode is a detector actually. It is used in optical fiber communication and TV detectors and fire alarms. Many are there. Many examples are there. Next one is solar cell. It converts solar energy into electrical energy. So we have best example Masdar city, Abu Dhabi. Masdar city. It's a best example for solar cells. Okay, it's one of the biggest. I think it's a world record again. Yeah, biggest power that is solar power plant in the world. Okay, it is generating solar energy from the solar energy. It is giving solar energy. Now, okay, we'll come back to the N-type. Then first we'll discuss about the temperature thing. I want to discuss about the temperature thing, which is very, very important. Then we will discuss about how what is Ni, Na, Ne and NH. Ni means intrinsic, Ne means number of electrons, NH means number of holes. Okay, this we need to discuss. Okay, this will be first of all we'll finish off this one. Then we'll discuss about the p-n junction diode. Then its VA characteristics. Then we can go ahead with this special types of diodes. Zener diode is not there, so no need to worry. So we'll only, I think hardly only four topics are there. Now, so before that we have, as I told you yesterday, see here for a N-type semiconductor. Yeah. So for N-type semiconductor, so for germanium, I told you on that day, for germanium and silicon, germanium it is 0.01 electron volt. How much is the energy required? How much is the energy required to move the electron from the valence band to conduction band? Okay, some energy is required, right? So why do we require energy? Again, we are using the same principle. V is equal to, keep that in the mind, V is equal to W by Q. So W is equal to VQ. Okay. So that is why we are writing in terms of electron volts instead of writing joules. When we are speaking about 1 electron, 2 electron, few electrons, we speak in terms of electron volts. Okay, because it is very easy. Because one electron accelerates, then it is known as like 1 electron volt. Okay, when one charge accelerates in the presence of one potential difference of 1 volt, then we say 1 electron volt. Okay, anyways, that's a definition in the second chapter. So we are not going to go ahead with that. Just explaining this. And this is the silicon. For silicon, it is how much? 0.05 electron volt. Now the energy gap. The energy gap for germanium. The energy gap for germanium, it is found to be. Now, so here the crystal maintains an overall charge neutrality. See here, generally when you speak about a crystal, like I have taken a crystal, like you might have studied this in chemistry. There is crystallography or solid state chemistry. Yeah, you discussed about crystals, Fresnel defect, Schottky defect. Yeah, you studied about all these systems, right? So we are starting from there. Actually, the semiconductors will start from there exactly, from solid state chemistry. In physics, we have solid state physics. The same exactly, same topics. Concept is same. Only name is different. Physics and chemistry. But here they speak about the crystals, FCC, BCC, packing fraction, and all those things they discuss, right? So we are starting from there now. So there is in crystal has a neutrality. Okay, overall charge and neutrality. A crystal, if you're speaking about a silicon or a germanium, if I'm speaking about a crystal like example silicon and germanium, it has a neutrality. What is that? Overall charge neutrality. Okay, overall charge neutrality. It has overall charge neutrality. Okay. Now, so as the charge of additional charge is just equal and opposite to that of the ionized core in the lattice. Okay. So what he is saying, additional charge is just equal and opposite to that of the ionized core in the lattice. So now you know what is lattice and all. I am not going to explain this. This is in chemistry. Okay. Now here Ni is what here? Ni is said to be number of intrinsic electrons generated. Number of intrinsic electrons generated. Suppose when we are doping, okay, when we are doping, what happens is ionization will take place. Okay, yes, polarity or ionization, such type of things take place. Okay, now, so now Ne is what? Ne is number of electrons, and NH means number of holes. Number of holes. Okay, so if you speak about an N-type here, in N-type semiconductor, what we have here, number of electrons are much greater than number of holes. Okay, already you know that. Ne means number of electrons, and it means number of holes. Number of electrons are much greater than number of holes. Okay, so now what is happening here? If you take a small, I'm just taking a crystal lattice to just make you explain. Suppose these are the positive, that is the holes you think. Okay, now this is the electron. So this is said to be a core donor. Okay, this is said to be a core donor. Okay, so here Ni number of intrinsic electrons generated, and Nth number of holes. So here what is happening in core donor? So N-type, excess number of charge carriers are electrons. Okay. Now we'll go to P-type semiconductor. What exactly is happening in P-type semiconductor? In P-type semiconductor, here what happened? Number of holes are much greater than number of electrons. Yeah.
So in the diagram you show, right?
Yeah.
So holes are greater than electrons.
So what is happening? You know, that there are excess electrons are coming in now. Excess electrons are coming in. There is a charge neutrality is there in the crystal. Number of electrons and number of, we say, ion protons or what holes are equal. But now what is happening? Excess electron is coming in. Understood? Because of the doping process. Okay, that we are trying to explain. That's it. Okay. Now here what is happening here? Now means now here this is all negative. Yeah, I'll write, just make it positive. Okay, so here all negative, and then what happens? A hole is there. This is a hole. So this is said to be acceptor core. Okay, so in thermal equilibrium, what will happen? Ne into NH is equal to Ni square. Okay, Ne into NH is equal to what? Ni square. Okay, in thermal equilibrium. Thermal equilibrium means what? At a particular temperature, number of electrons and number of holes are exactly equal. Okay, thermal equilibrium. You know what is a thermal equilibrium, right? In thermodynamics, you might have studied this word, thermal equilibrium. Suppose if you keep a coffee or tea, which is at 65 degrees centigrade, and you leave, the room temperature is 25 degrees centigrade, and you leave it for some time, what will happen? Maybe after 5 minutes or 10 minutes, the temperature of the coffee will come down. Your tea or coffee will come down. It doesn't become 30. Like the room temperature will not rise, right? Room temperature is not going to become 37. Room temperature maximum, it can not even 1 degree, not even half degree, not even 0.1 also, because the volume of the room is much greater than the volume of the coffee. So the coffee will come down, the tea will come down to lower temperature, room temperature slowly. Okay, so that temperature is said to be thermal equilibrium. Understood? That means both of them will come to a same temperature.
So can you explain this diagram again?
See what is happening in the core donor. In the core donor means what is happening here? This is N-type semiconductor. So what happens? Electron is added to the excess electrons are there, right? In N-type semiconductor.
Excess electrons.
This is the excess electron, like Frenkel defect and Schottky defect. If you can have a little idea about that, Frenkel defect and Schottky defect. What is happening?
From the
yeah, exactly. A displacement of electron. In one case, I don't exactly remember. In one case, the electron will dislocate. I think something.
Schottky effect.
The second one, what is that?
Frankel is the extra electrodes of the
Something like that. If you have an idea of Frankel defect and Schottky defect, then you will understand this process. Understood now?
Where there is more electrons.
Yeah, excess electron. One electron has come in.
Okay.
Means it is an intruder. Okay, here one electron left actually. Because of that, a hole was created. Understood now? So for that, please do just once again revise quickly that Frankel and Schottky defect. You will understand this. This is the first example of that.
So Frankel means there are excess electrons. Schottky means one electron is
dislocated something.
So one cation is displaced.
So this is same process actually. Understood now?
Yes, sir.
Clear, sir? Aman? Yeah. Now in thermal equilibrium, what we are saying, Ne into NH is equal to Ni square. What is the meaning of this? In thermal equilibrium means, intrinsic means pure man. Intrinsic means pure. So Ne into NH is equal to what? Ni square. Okay, that's the thing. Yeah, what is that? Interstitial. I didn't get what is it.
Sides, yeah.
Yeah, interstitial.
Interstitial sides.
Yeah, exactly. So I'm not good at chemistry. Okay.
So can you explain this thermal equilibrium?
Thermal equilibrium is what happens when the suppose you have taken a semiconductor man. Maybe it is a p-type semiconductor and an n-type semiconductor. It is in thermal equilibrium. In thermal equilibrium, what will happen? Ne into NH will be equal to Ni square. If you take a pure material, if you take a pure semiconductor, number of intrinsic are Ni. Okay, but if you are taking an impure, like maybe a p-type semiconductor or n-type semiconductor, number of electrons and multiply number of electrons into number of holes. That will be the square of the intrinsic. Only this can be applicable only when there is thermal equilibrium in the situation. Understood now? Got it? Chalo. Next we will go with
That's for p-type.
No, this is for both.
Common.
It is common for both thermal equilibrium. Okay. Now, is it clear?
Yes.
Chalo. What about you, Mr. Johan Joshua? Yes, Ibad. Okay. Now, actually the teachers will not explain much in this area. They just go quickly to p-n junction diagram. They just give the classification and they directly go to p-n junction diagram. I think the same also everywhere they are only explaining types of semiconductor. Directly they will explain p-n junction diagram and all the remaining. This is actually crux. This is the transition actually, where exactly you will understand the phenomena. Okay, so if you have some time, crystallography is first term or second term? Crystallography, chemistry. First term. If you have little time, just go through that crystals once again. Okay, the lattice thing, the Frankel defect, the Schottky defect, just go through that. Then you will understand this better. Okay. Now energy levels. I'm explaining this Fermi level and all. Okay. So energy bands. Energy bands. So you can see these are the levels. Now these are the electrons. Okay. So this is a donor energy level or Fermi level. Okay. And this gap is said to be energy gap. This is a gap is said to be energy gap. EV, energy of the valence. EC, energy of the conduction. And this is the electron energy. This as going up. Okay, the energy of conduction is greater than the energy of the valence. Okay, and this is the dotted line is the Fermi level or donor energy level. For electrons, we say donor. For holes, we say acceptors. Donor and acceptor. So that's what I'm saying. Just if you have a little time, go through the solid state chemistry once.
So here in EC, there are more number of holes than electrons, right?
Number of
EC.
Yeah, EC number of
Holes are more than electrons.
I don't think so. It is n-type semiconductor. This is N, not P. This is N. More number of electrons, no? Except number of charge carriers.
So then EV means there are many valence electrons over there.
Valence electrons. Just one second. Let me see once again the diagram. He didn't mention anything outside in this one. He didn't mention anything. See, if you go to the this is n-type. Okay, it's not even mentioning this also. It's a means if you give little energy, now this line is very close, right? This line is very close to conduction band. Means all this, the meaning is what? All this electron is just below this area. This energy is all the same. This energy is same. If you give little energy, it will immediately jump into the higher energy levels. Understood now? So got it now?
So
But
this is for N-type.
N-type. This I write here. This is for N-type. Okay. N-type semiconductor. So we have this is the energy level diagram. Okay. And for P-type, the thermally generated electron pair, the field electron. No, we can't say exactly. Wait, one second. No, this is not N-type and P-type. Before I have already explained. This is about the temperature thing. Not
We have
N-type.
already drawn this.
No, that already we drew, right?
Yeah.
That is a different thing. That was here. Okay, this is about the temperature, man. When T is equal to 0 Kelvin. This I am discussing about the P is equal to the temperature dependence. You understood? Now think that the temperature, this is what is happening, Okay, I'll remove this also for your understanding. I'll remove this. I went in the other way. Not N-type and P-type. I am discussing about the temperature dependence of the thermal equilibrium. Okay. Now, suppose the temperature is 0 Kelvin, man. 0 Kelvin means how much? Minus 273 degrees centigrade, right? This is my temperature now. At that time, all the electrons, almost all the electrons are in the ground state or what we say is valence energy level. Okay. Now what will happen is when T is greater than 0, when you increase the energy, okay, see, when we just increase the energy, what will happen? This is EV and EC, same. This is EV and this is EC. So now what will happen? This is energy gap. This is the energy gap. So when T is greater than 0 Kelvin, okay, when T is greater than 0 Kelvin, so what will happen? Electrons will jump here, okay, by creating holes here. Okay, electrons will go here by creating some holes. Okay, clear? So that's what he's saying. Okay, got it now? Electrons are jumping from valence to conduction band when temperature is changing. So more you don't think that, sir, I will increase the temperature. No. Then the property of semiconductors will change. So that is why your computers or the electronic devices will not function properly at high temperatures. Understood? So suppose if I am buying most of the computers that we go to computer lab and all in India, generally there is no AC, but AC is there only working in computer lab. Why? Because it needs these the components, electronic components, they require low temperatures. Otherwise, the property of the computer will change. Understood now? The properties of electronic chips or something, it will change. Okay, components will change. Now, here it is. This is N-type and P-type semiconductor. This one.
Yeah. When T is equal to 0 Kelvin, there will be electrons in the.
All the electrons within the valence shell.
So when it's greater than 0 Kelvin, it will become holes.
Electrons are going up but leaving the vacancy there.
So it will become holes.
Hole. Whenever a vacancy is created, there is hole. Okay. Now we will discuss about the N-type and P-type semiconductor. Energy level diagram for N-type and P-type semiconductor. Okay. Then we can directly go to this P semiconductor. Okay. Clear, sir? Yes. No. It will be same diagram only, but just I will draw the Fermi level here. Okay. Here there is a Fermi level. This is ED. This is T greater than 0 Kelvin. T greater than 0 Kelvin. This is N-type. This is the second one is P-type. same. It looks like the same. Okay. It looks the same. So here EC and ED. This is how much? 0.01 electron volt. 0.01 electron volt. And here there is a donor. Now, coming to the second one. Here, this is the acceptor energy level, EA, I think. EA, I think. Yeah, EA. That is 0.01 again. This is also 0.01 electron volt to 0.05 electron volt. Okay. Clear? 0.01 to 0.05. So now what is happening? You know that here this is for N type and this is for P type. For both P greater than 0 in both the situations. Now what happened? Here electrons are the charge carriers in N type semiconductor and the holes are the charge carriers in the P type semiconductor. And here the Fermi level is very close to the conduction band. Means if you give little energy, electrons are ready to flow, conduct the current. They conduct current, only not AC, only DC. Whenever there is a semiconductor concept, only you are applying DC current, no AC current. No AC current is applied. Understood? Okay. So because only current electrons can flow in one direction. Now what is happening here? So electrons. So it means if you give little energy, electrons are ready to flow to the higher level, to the conduction band. So how much energy is required? Only 0.01 electron volt. That much energy is required. Understood? But coming to p-type semiconductor, the holes are the charge carriers. Holes are the charge carriers. Means holes have to move, right? Yeah? Holes are the charge carriers. Means what? If holes have to move, means electrons have to come in the opposite direction. Yeah? Electrons have to come in the opposite direction. That means this electron have to jump here, right? Then only the hole will be created there. Clear? So that means the energy is how much here? 0.01 again, but that is not with the conduction band. This is with the valence band. Exactly in the opposite direction. Understood? Yeah. So
then valence band is more negative charge, right?
Valence band, we cannot say negative charge. It is the place where all the electrons lie actually.
So then it would be more energy required for the electrons to jump from.
Yeah, exactly. It requires more energy for the electrons to jump from the valence band to conduction band in p type. So that is why we are moving the holes. The other way, what? We are moving the electrons in the opposite direction. Understood now? So this is a problem here. 14.2. Please do try this question. 14 points. Then we can directly go ahead with the PN center. This is 14.2. Please take a picture of this and send it to them in the group also. Please do try this question.